Alright, this video is for Algebra 3-4 Extended. We are going to review how to write the equation of a trig function based on its graph. So I'll do a few examples of this, and then I'll go back and I'll do a couple of examples of the sinusoidal applications. So let's do this problem here. This is number 14 from your packet. So remember, I'm going to ask you how to write this function here, both in terms of sine and cosine. And remember, there's going to be a bonus point if you can identify a different version of each. So let's go ahead and just take a look at this number 14 right here. If I asked you what would be one thing you knew about this graph, the first thing you should probably identify is the vertical shift. So we know that we're going to be required to write this thing in terms of a sine, and it's also going to have to be in terms of a cosine. And so since the vertical shift is 2, I can go and throw a plus 2 on both. Remember, the only thing that changes for sine and cosine would be its phase shift, and then whether or not the phase shift incurred a plus or minus. So really everything else is just kind of identical, so this is not particularly hard. So let's see, let's go ahead and find the amplitude after that. Well, we know that from 2 it goes all the way up to 6 and down to -2. That means that the amplitude has to be 4, because from the 2, it moves up 4 spaces to get to its highest point and down 4 spaces to get to its lowest point. That's why the amplitude is 4. So from here, we can go and try and find the period. Now the period, remember, is identified as from one peak all the way to the other peak. So we have to figure out what distance that is. Well, the distance is 5 pi over 12 all the way to -pi over 12. So really, if I was to find the distance between the two, it would be 5 pi over 12 minus -pi over 12, which is 6 pi over 12, which is really pi over 2. Now, where people are going to make their mistake is they're going to plug a pi over 2 straight up into here. That is not correct, because this is the period of the function, but the period in and of itself doesn't tell you anything. You use the period to find the frequency. And the frequency is going to be the normal period of this function, whether it's sine or cosine, it doesn't matter. The normal period is 2 pi, and we're going to divide that by pi over 2. So what you'll find is that the 2's are going to actually multiply together, and the pi's are going to cancel each other out, giving you 4 pi. Oh, just kidding, just 4. And if you don't believe me, check this out. 2 pi divided by pi over 2 is the same thing as 2 pi times 2 over pi, because you just flip the second and multiply. Goodbye to the pi's, you get 4 after 2 times 2. So the frequency for both functions is 4. And now you just have an x, and now you just have to figure out where your phase shifts are going to happen. Well, cosine is a piece of cake. I can either shift it to the left by pi over 12 by saying plus pi over 12, or I can shift it to the right by 5 pi over 12 by saying -5 pi over 12, or I can shift it to the right by pi over 6, and if I did that, then cosine would have to be negative. So why don't I go for the easy one, and I will just shift it to the left by pi over 6. Remember, when change occurs inside parentheses, it's opposite your intuition, so we're going to add pi over 6 this time. The hardest part is actually finding out the value of sine, the phase shift of sine. So if I look at the bottom here and I look at the top, I'm going to want you to understand that this x here is going to be halfway between them. So all I need to do is I need to average out -pi over 12 plus pi over 6, so that's oops, wrong color. That would be -pi over 12 plus, now pi over 6 I'm going to call 2 pi over 12. Just for common denominator's sake. That's going to give me pi over 12. Now, 1 pi is an odd number, so I'm going to multiply it by 1/2. I would have done that anyways, but since pi is only one of them and it's an odd number, I have no choice but to multiply the bottom, and I get pi over 24. Since I'm moving to the right by pi over 24, I'm going to be subtracting that value. And there are your two versions of this function. Okay, let me pause for a second and grab the next one. Okay, here comes number 9. So, as we look at number 9, the the process still stays the same. I'm gonna have you write this once as a sine function, and then once as a cosine function. Again, vertical shift is really easy to find. It's going to be -2 for both because we're shifted down 2. Now, to find the amplitude, I'm going to find the distance between the vertical shift and the highest point and the lowest point, and since these are symmetrical, they'll be the same. It looks like the amplitude for this function is going to be 5. Now, to find the period. Well, notice how I don't have any increments of measure in this one. So since I don't have any little degree signals, this -20 and this -5, I'll assume that it's in radians, and you should too. So, what is the period of this function? Well, the period, if I go from peak to peak here, the distance between them is 25 minus -5. So that is 25 minus -5. That is 30. Now, the distance is the period, but remember, the period doesn't tell me much. I need to use that period to find the frequency, which is 2 pi divided by 30, which is the period found. So it looks like I get pi over 15 as my frequency. Oops, it's not a very good 5. Okay, so now I just have to figure out where my phase shifts are going to come from. Well, again, just like the last example, cosine seems pretty easy. I can either phase shift it to the left by 5, or I can phase shift it to the right by 25. I can phase shift it to the right by 10 and make it negative. Bunch of different options. Just for variety's sake, I'll go ahead and shift it to the right by 10, and I'll make cosine a negative value. Again, it's your choice. Just like the last example, finding the phase shift of sine is going to be a little harder. And so why don't we go ahead and try and look at this peak to this valley. Again, you could have chosen any one of them. It doesn't really matter. I'm going to go ahead and find out where this intersection point is. So it looks like this occurs at -5. The peak occurs at -5 and the trough occurs at 10. So I'll go ahead and average those two values together. So 10 plus -5 divided by 2, that's going to be 5/2. So I'm going to go ahead and subtract 5/2 from my x value so that I can get to the right by this much. Now, if I do that, sine must also be negative. Okay, cool. Let me get one last example and then we'll move on to some sinusoidal applications. And the last one we're going to look at is number 2. Now, the first thing you want to notice about number 2 is that, the measurements for the x-axis is in degrees. And so you want to make sure you're paying attention to that so that you can use the right measurement for your frequency. And so I chose this one because it is in degrees, and I want to give you guys some variety, variety being the spice of life. So again, but despite all the variety, we're still going to be able to, we're still going to have to use kind of the same pattern here. We're still going to identify a sine. We're still going to identify a cosine. The vertical shift is -30. I got that from this black line right here. My amplitude is 10. Because from -30 it goes up to -20 and down to -40. Now it's time to find the period. It looks like the period is going to be from here all the way to here. So I'm looking at 13 minus -7. So that is 20 degrees is my period. All right, I kind of bypassed all the work right there. Now, here's where people are going to make their mistake if I put something on the quiz like this. People are going to take 2 pi and divide it by 20, and they're going to get pi over 10, and they're going to get that wrong. Remember, this is working in degrees. So, in this case, the normal period of sine and cosine is not, in fact, 2 pi. It is actually 360 degrees, because there are 360 degrees in 2 pi radians. So, I'm going to take the 360 and divide it by the period found. I end up with 18. And that is what goes inside my frequency. All that's left is to find the phase shifts. I believe this one is relatively simple. Cosine, I'll go ahead and shift to the right by 3, and sine, I'll shift to the left by 2, and you're all done. Alright, so let me go ahead and move on to some applications of this. So right before you left yesterday, I asked you guys to handle the bouncing spring problem. I don't remember if we actually did that one in class to review, but let's just do it again, why not? It says, a weight attached to the end of a spring is bouncing up and down. As it bounces, your distance from the floor varies sinusoidally with time. You start the stopwatch when the stop reads 0.3 seconds. The weight reaches the high point of 60 centimeters above the ground. Let's see what that looks like. First thing we're going to do is we're going to sketch a graph of this sinusoidal function. So part A, we're just graphing it. So I'm going to go ahead and just draw my cool horizontal line here. And the problem again reads that when I'm at 0.3 seconds, so let's go ahead and just mark this as 0.3, your weight reaches the high point of 60 centimeters off the ground. So again, these are almost like the things we just did, except now they're just asking you to graph it. Also, to construct the graph, they're not giving you the graph. And it says the next low point is 40 centimeters above the floor, which occurs at 1.8 seconds. So 1.8 seconds, whoops, 8. It hits its lowest mark right here, which is 40. And so because this thing is said to vary sinusoidally with time, we can say that at some point it will reach the exact same height as before. Again, forget about inertia and all that stuff that's going to keep the spring from bouncing up exactly as high. This is just a model. We can say that because 1.5 seconds occurred between 0.3 and 1.8, another 1.5 seconds occurred to the next time period, which means this is going to be 3.3 seconds. If we were to graph this thing, it would most definitely model a cosine graph, where my vertical shift is going to be 50, and the way I got that is I averaged 60 plus 40, and then I divided it by 2. 100 divided by 2 is 50, so that is what is giving me this vertical shift right here. Cool, I think that is the graph of this sinusoidal function. Now we have to write an equation that fits this curve. The equation, well, now we're just back to the last couple of examples. Y equals, now remember, with these problems you only have to write one. You're not required to write one for sine also. So I'm just going to, this looks like cosine, which is pretty obvious. And I know that my vertical shift is 50. And I know that my amplitude is 10. And all I have to do is figure out what the period is. Well, the period is 3 seconds. And because they don't give me any kind of degrees or anything like that, I can assume that I will be measuring my frequency by radians. So my period is 3 seconds, which means my frequency is going to be 2 pi over 3. So 2 pi over 3 goes here, and now I just have an x minus 0.3. And there you go. That's full credit for part B. Now, part C says, what is the distance from the floor when you started the stopwatch? Well, when you start the stopwatch, the time will read 0. So what you want to do is you want to say y equals 10 cosine of 2 pi over 3 times, since we started the it started the experiment at time equals 0, it'll be 0 minus 0.3 plus 50. Now, negative 0.3 is like negative 3 over 10. I will leave it like that. And I'm going to multiply that by 2 over 3 pi. And I'm going to say plus 50. And I've got this 10 cosine here. Y equals 10 cosine 2 pi over 3 times negative 3 over 10 plus 50. And now I'm just going to go ahead and simplify everything. Goodbye to the 3's. I can kill off the 2 with the 10 and end up with a 5 on bottom. Now, I will not let you use a calculator for this test, which means all you have to do is leave this thing in calculator-ready form, which will be 10 cosine negative pi over 5 plus 50 centimeters above ground. And you circle it, and you move on. Let's check out another problem real quick. Okay, the last problem I'm going to do is the tsunami problem. Now, I cut out D in this problem because I realized that in order for you guys to solve D, you guys need to be able to solve trig equations, and we haven't gotten there yet. So At some point, we'll revisit some of these sinusoidal applications, and I'll show you guys how to solve D. But for now, go ahead and just solve for A, B, and C. A tsunami, commonly called a tidal wave because its effect is like a rapid change in tide, is a fast-moving ocean wave caused by an underwater earthquake. The water first goes down from its normal level, then rises an equal distance above the normal level, then finally returns to the normal level. The period is about 15 minutes. Suppose that a tsunami with an amplitude of 10 meters approaches the pier at Honolulu, where the normal depth is 9. Assume the water varies sinusoidally with time. Part A, obviously, we need to sketch a graph of this model. So, we're in Honolulu. The normal depth is 9. Now, you have to watch the behavior of the tsunami. It says, first, the water goes down from its normal level, then rises an equal distance above its normal level. And it tells you that the amplitude is 10 meters. But, given the fact this is the last problem, it's surprisingly the easiest one. Since the amplitude is 10 and your normal level is 9, I hope it makes sense that your maximum height will be at 19. And then your minimum height will be at -1. When they talk about the water first going down from its normal level, you should have seen this happening. Down from its normal level, then up an equal distance above its normal level, and then coming back down to its normal level. This is upside down sign. And so it says, it even gives you the period. It gives you the period 15 minutes. So this is 15 right here, where this is 0. And from here, you just have to, this is A. It's done. And so now you have to figure out B, write an equation to fit this model. Well, obviously, it's an upside down sign, so it's negative. My amplitude is 10. Sine. I'll go and leave this blank for now, and I know this is going to be plus 9. The period is 15 minutes. Which means that my frequency is 2 pi over 15. And it's going to be x. Looks like minus nothing, so you can either write x by itself and just close it off here, or x minus 0, x plus 0, it doesn't matter as long as it's just x. Okay, that was part B. That was easy. Let's take a look at part C. It says, predict the depth of the water 12 minutes after the tsunami hits. Okay, so here's what I'm going to do. I'm going to let x equal 12. And so, unfortunately, like the bouncing spring problem, without a calculator, I can't really figure out directly what this thing equals. We're not used to dealing with pi's over 15. I'm just going to let this thing equal 12, and I'm going to put a plus 9 out there. I'll just multiply those in, and I'll just say y is equal to negative, not negative sign, negative 10 sign of 24 pi over 15, no need to reduce that, don't worry about that, plus 9, looks like meters from normal. Now, I put meters from normal because at this point, sine could either pop up in either the positive quadrant or the negative quadrant, so you don't really know how far away this thing is. And so just to be safe, just write meters from normal. Because if you write above and it's actually below, then technically your answer is wrong. Okay, so those are your problems. I hope you were taking notes, and we will see you on Friday for the quiz.